Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on time series analysis, the basics of time series analysis. And for this particular lesson, I will illustrate the basics of time series analysis with a particular data example. Reports from different countries, including the United States, the United Kingdom, China, and other countries, have shown an increase in demand for emergency department care, resulting in frequently overcrowded EDs, lengthy waiting times for assistance, and an overall perception by patients of poor health care. Prolonged waiting times are described as a major factor for dissatisfaction with ED care, and patients are more likely to leave without being seen as waiting time increases. While common practice is to using data on daily patient volume for better planning of personal resources might increase ED efficiency, as well as improve ED patients' care quality. Time series models can be used to forecast future ED patient visit volume based on the estimated effect of predictor variables, and such forecast can be used for proactive bed and staff management and for facilitating patient flow. A number of factors can influence daily ED visits, and the patient's visit forecasting model should include those factors. Previous studies have shown that ED visits present cyclical variations according to calendar variables such as day of the week, time of the year. The objective of this analysis is to develop models for identifying temporal patterns and for predicting the volume of patients in an emergency department. The data consist of daily number of patients seeking ED care in a hospital in Georgia in the United States. The ED volume was observed over a period of more than 5 years from 2010 until about mid-2015. And the study will only consider temporal factors, although other factors can be used. For example, external factors such as temperature, rainfall, major holidays such as school season, among others, along with hospital data, for example, the percentage of patients seeking care in ED who have public insurance versus commercial insurance, among others. We'll begin with one important aspect in a time series analysis, processing time or dates of the observations. The first step is to read the data in R. The command used here is read.csv, used for reading CSV data files. The input consists of the data file and specification where the columns in a data file have names. Since this is the case for the data file we read, in R, we specify header equal T or true. The data columns include year, ranging from 2010 to 2015, month, taking value 1 to 12, and day of the month along with the column volume, providing the number of patients seeking care in the ED for the corresponding day. The first 3 columns provide the complete information on the dates the observations were made, but because the information is provided across the 3 columns, it needs to be converted into one column of dates to be used in visualizing the data. To do so, we pull the 3 columns into one matrix. I define here a function paste_dates, which takes as input a vector of 3 variables, day, month, and year. The function returns a date using the information from these 3 date factors. I apply this function to each row in the date mat to output a date for each row in this matrix. Last, I converted the dates as output from this R command into dates that R can identify as such using the asDate command. This vector of dates will be the input into the visual analytics displays to display time. A first plot of the time series is the plot of time expressed as dates provided in the previous slide, and the values of the daily ED volume. And few observations to point out are as follows. There is a generally increasing trend in the ED volume. There is some cyclical pattern, although not necessarily a seasonality, since it does not repeat at exact periods of time. And there's some clear outliers, for example, beginning of 2011 and in 2014. I will note that count data within a time unit, such as the number of patients seeking care per day, has a Poisson distribution. But the standard linear regression model employed to estimate trend and seasonality assumes normality with mean varying over time, but constant variance. One of the limitations of using the standard linear regression model under normality to model count data is that the variance of the error terms is non-constant, and thus a departure from the model assumptions. In order to use this model, we thus need to transform the data using a variance stabilizing transformation. That is, transform the count data or Poisson distributed data such that the data have approximately constant variance. The transformation has also the role of normalization of the count data. The classic transformation used for count data is the square root of the counts plus 3/8. Thus, we apply this transformation to the count data and provide the time series analysis on this transformed data. We next compare the histograms of the ED volume and the transformed ED volume to evaluate the distribution without and with transformation. These are the histograms. The first one is for untransformed, and the second one is for the transformed ED volume data. The transformation has also the role of normalization, since with this transformation, the distribution is approximately symmetric. This slide compares the time series without in the upper plot versus with transformation in the lower plot. The pattern is generally similar, with trend and cyclical trend and outliers at similar time points. The main difference is that there is a reduction in the variability. In this lesson, I introduced a data example that will be used to illustrate the basics of time series analysis. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on basics of time series analysis, and in this lesson, I will introduce a trend and seasonality estimation with a data example on modeling ED volume. Let's begin with the estimation of the trend. I applied here only non-parametric estimation approaches, the local polynomial and the splines regression methods. Similarly to the Atlanta temperature data example, we need to first define the data points, the time points, which are simply equally spaced values between 0 and 1. Then I applied the R commands LOES for local polynomial and GAM for splines regression. I am overlaying here the estimated trend from the two models for the transformed ED volume data. In brown is the local polynomial trend, and in red is the splines regression trend. The plot is here. The trends are similar. They both show an increasing pattern over time with some smooth variations over time. The splines regression trend shows more variation, capturing some of the cyclical pattern. This is the output of the summary of the fit using splines regression. First, the p-value for the statistical significance of the smooth term of the trend is statistically significant, indicating a statistically non-constant trend. Second, the adjusted R-square is 0.296, implying that about 30% of the variability in the ED volume is explained by the trend alone. This is the resulting plot. We can see that the fitted values are a step function. This is because I fitted the seasonal means model. The fitted line in red does capture the trend. However, the seasonality shows differences from the observed data in some places for some periods of time, indicating that they may be more of a cyclical pattern than a monthly seasonality. Moreover, the monthly seasonality may be more related to other factors than the month. For example, school seasons or flu seasons may be more predictive of the cyclical pattern. Next, I'm adding another layer of seasonality due to the day of the week. It may be expected that on Sundays to see a higher volume in the ED since the physician offices are not open and because people may have more activities that could lead to injuries and hence ED visits. For this, we need to first identify which of the dates correspond to Mondays, which correspond to Tuesdays, and so on. A simple way is to use the weekdays command in R, where the input is an object derived using asDate command. I'm converting this into a factor to specify this is a categorical variable. Starting with the model where I fitted the trend and monthly seasonality alone, I'm adding an additional linear term, the categorical variable corresponding to day of the week seasonality. Last, I compare the two fitted models by overlaying the fitted values from the two models, where the red line corresponds to the simpler model with monthly seasonality only. Here's the plot. The fitted line, including both monthly and day of the week seasonality, clearly shows the added seasonality due to the day of the week. Altogether, estimated simultaneously, the monthly seasonality is picked up somewhere better. This is a portion of the summary output of the model, including non-parametric trend along with the two layers of seasonality. The first portion of the output shows the estimated coefficients for the monthly seasonality. In the first column, we have the estimated coefficients. In the second column, we have the standard errors. And in the last column, we have the p-values for statistical significance. From this output, we found that most of the regression coefficients corresponding to the monthly effect are statistically significant given the day of the week seasonality and the non-parametric trend in the model. The second portion of the model output shows the estimated coefficients along with the p-values for statistical inference for the day of the week seasonality. From this output, we find that some of the regression coefficients corresponding to the day of the week effects are statistically significant given that monthly seasonality and the non-parametric trend are in the model. The output for the trend also shows statistical significance of the smooth component given the seasonality in the model. Last, the R-square is 0.627 or 62.7% of the variability in a time series is explained by the trend and the two layers of seasonality. This is to be compared to 0.296, the R-square for the model where only the trend was fitted. From the previous output, we found that for both layers of seasonality, there is statistical significance for some of the regression coefficients. The question that we'll address next is, does the day of the week seasonality add predictive power to the model? For this, we'll compare the models without and with this layer of seasonality. I thus fitted a linear regression model with both layers of seasonality and the model with only monthly seasonality and compare them using the partial f-test through the command ANOVA in R. The input in this command consists of the two models. The output of the ANOVA command is here. The p-value of the test is very small, indicating that we reject the null hypothesis that the simpler model with monthly seasonality only is as good as the one with both layers of seasonality, suggesting that both monthly seasonality and day of the week seasonality are predictive. I'm comparing the fitted regressions without and with trend to assess whether trend indeed adds any additional predictive power. And this is the plot. In black is the fitted regression for the full model. The one in blue is for seasonality with the two layers excluding trend, and the one in red is the fitted trend alone. The trend does impact the fit significantly, thus the full model provides the best representation of the non-stationary components of the time series represented by ED volume. In this lesson, I introduced estimation of trend and seasonality for a data example where we're interested to model the emergency department volume of patients. Thank you. This is a time series analysis course. My name is Nicoleta Serban. I'm an associate professor in the Stewart School of Industry and System Engineering. The lecture is on basics of time series analysis. And for this lesson, I will continue with the data example for modeling the ED volume of patients. And we will continue with analyzing the stationarity of the residual process after removing trend and seasonality. Here we'll compare three residual processes. First is the residual process after removing the trend alone. Second is the time series after removing seasonality, including monthly and day of the week. Third is the residual time series removing both trend and seasonality. The first R commands are to obtain these three residual time series. Next, I define the minimum and maximum values across all three processes in order to plot those time series on the same scale. The next set of R commands plot all three residual time series, overlaying them into one plot. And this is the resulting plot. In black is the time series after removing the trend alone. In blue is the time series after removing the seasonality. The time series in black clearly have some unstationarity patterns, while all three have outliers. To better evaluate the stationarity of a time series, we can instead evaluate the autocorrelation plot of the time series. Here I'm providing the R commands for the sampled autocorrelation of all three time series. The first one is for the residual time series after removing only the trend. An indication of non-stationarity is that the sample autocorrelation is large or outside of significance bands for many large lags. This is the case here. We see that even for a lag of 45, the autocorrelation barely drops within the band. Moreover, we can see a pattern of ups and downs, an indication of seasonality. The second one is for the residual time series after removing the seasonality. While we do not see the cyclical or the seasonal pattern in the ACF values, the sample autocorrelation decreases slowly, an indication of the presence of a trend in this process. Last ACF plot is for the residual time series after removing the seasonality and the trend. The sample ACF values clearly decrease faster than for the previous residual time series, with small values within the significance band starting around the lag 15. This is an indication of possibly a stationary process. We'll expand more on stationarity based on the ACF plot and more rigorous ways to evaluate in a different lecture. I will conclude with some findings from this time series analysis. Some of the findings from the study are as follows. There is a significant increasing trend in the emergency department patient volume over the past 5 years. The seasonality is more complex. Both monthly and day of the week are statistically significant. There are cyclical patterns that may not be fully captured by seasonality. Other cyclical factors such as flu season or school season may explain the cyclical pattern. With this lesson, I concluded the data analysis for the ED patient volume. Thank you.